Thank you very much. So first, I would like to thank the organizers for giving me the chance to talk here and for bringing us all to Korea, I think for many of us for the first time. So yeah, I'm going to talk about the singularity structure of Feynman integrals. Maybe. No. Well, not more success for that. So, yeah, so with not Jake's pointer, this talk will be based on 3 papers that I published together with Martin Helmer and Georgios Papathanassiou. This is indeed a very old story, dates back to 1959 by the papers of Landau and Nakanishi. But I also wanted to highlight here this paper by Pham, which is a very different mathematical approach to this story. This has now been written up in several books. You have seen the S-matrix book several times, and I will show it here again. But I also want to highlight the book by Todorov. Nakanishi has also written a book on graph theory and Feynman integrals. And some lecture notes by Frederick Pham has been compiled into this book on singularities of integrals. But around 15 years later, in the mid-70s, Feynman integrals and the S-matrix was picked up by the Japanese D-module school by Kashivara and Sato and Kawai and so on. And this, of course, is extremely mathematically rigorous. These are not physicists, these are mathematicians. The problem with these papers is that despite all the rigor, there is, maybe due to all the rigor, there is no actual method here to calculate anything. They have good definitions for what the singularity is, but if you actually gave them an integral, I don't think they can actually tell you what the singularities actually are. But so it's in the flavor of, this will be the flavor still that I will work in the framework, but trying to make this explicit. There have, of course, been much more recent approaches than in the mid-70s, and I wanted to highlight just a few. So one way of calculating singularities is via polynomial reduction, and been implemented by Brown and Panzer. This was also very recently revisited by, for example, Miguel. They talked yesterday, and Kiko and Misera. Also wanted to highlight the principal A-determinant approach to singularities by Clausen, and I have also worked briefly on this. And also, a few years ago, an object called the principal lambda determinant was introduced to capture singularities. Last month, Matsubara Hyo introduced a new thing he calls hypergeometric discriminants to describe these singularities. Out of this list, there is one thing that should not be here, really, and that is the principal A determinant, because as a physicist, that actually only, when it works, it would only work at one loop. However, I think this description of singularities is the gold standard that we should all strive towards when it comes to understand the singularities, because it does 2 things very well. It gives us a full description of not just the singularities, but of the full characteristic cycle, and gives a very specialized method of calculating these things. And this first thing has now been achieved, I would say, by my work and also in this paper by Sayeh. And it's very funny that Sayeh and I managed to publish an archive on the same day without talking to each other about this fact. We have talked to each other half a year earlier about that we were both working on the same problem, and then we managed to publish on the same day. But none of us have really developed specialized methods to do these calculations yet. They both rely on very general mathematical framework. So let's start with an example, one of the simplest Feynman integrals. So let's look at the one-loop bubble in Lie-Pomeranski representation. We all know the lambda singularities with this one. It consists of 4 components, the vanishing of the 3 kinematic invariants and the vanishing of the Chilean function. This integral has 3 master integrals in general, and the number of master integrals drops by 1 on each singularity. And this information can actually be encoded in something called a constructible function. So now we do some almost pattern recognition. So you see that this 3 has something to do with the 3 master integrals. These varieties here are the components of the lambda singularities. And the minus ones in front of all of these things was the fact that it dropped by 1 on each singularity. What the EUs are, they are something called Euler obstructions, and we will come back to that. I just wanted to note that this function, as we have already seen in Anna-Laura's talk, when she told us about the holonomic rank of a D module. This is just a rank function of the D module that I had denoted here, integral of M. So this is the system of PDEs that annihilates this integral. This thing has an equivalent description as something called a characteristic cycle. This is an object in the cotangent bundle of the kinematic space. So once again, we carry around our recognition that's 3. Now it becomes 3 times the 0 section of this bundle. And similarly, the arguments just comes into these things denoted by con, which are conormal varieties. We will come back to the precise definition of these things later. And the ones are still just encoded in being ones in front of this. But I want to note that the constructible function and the characteristic cycle usually contains many more subvarieties of the singular locus than just the codimension 1 part. That is just the codimension 1 part here comes from the fact that this is secretly a generalized hypergeometric system. Okay, but this description of the singularities contains even more. So the characteristic variety of a system of PDEs is just the support of this thing we just looked at, the characteristic cycle. So just a union of all these conormal varieties in the cotangent bundle. If U is the solution to our system, so think of U as our Feynman integral, then the singularities in the cotangent bundle, here denoted WF or wavefront set, is a subset of this characteristic variety, and we say that U is microanalytic outside of this singular set, and therefore especially microanalytic outside of the characteristic variety. So if you describe singularities in terms of characteristic cycles or in terms of constructible functions, which are equivalent, then we get 3 things. We get the lambda singularities, we get the number of master integrals on and off singularities, and we know that the solutions to this system of PDEs will be microanalytic outside of this characteristic variety, which was just the support of the characteristic cycle. So our approach to get this construction is fairly straightforward. We just first want to construct or describe the singularities of the integrand itself. Then we want to find a map that can represent integration. And then we want to map the singularities of the integrand onto the singularities of the integral. So I try to depict it here schematically. So if we integrate this parabola here, it's of course singular where the parabola vanishes. And then if you just view integration as projection onto the z variable, all these singularities just gets projected down to a line. But there's actually only one singularity that survives, and that is the singularity where the arrow here also fits into the image space. And this has something to do that we should really think about this in the cotangent bundle. So this is the description I want to describe today. Find singularities of the integrand, find the map, and then just map the singularities. And the mathematical framework that we developed this is within Euler-Melin integrals. So 2 of our favorite representations of Feynman integrals are automatically here. We have the Lee-Pomeranski representation, we have the Feynman representation. The momentum representation is still a product of polynomials, so that's fine. It has the wrong integration boundary in the sense that it has no boundary at all. And one could also ask about Bykov, for example, but which also has the wrong integration boundary. But we believe that this can be accounted for, and then there is a more general theory here for actually every type of period, but we have not worked out the details for that yet. So the main concept here will be about stratifying singular varieties. So if we consider algebraic varieties of a C, so that is a variety X, which is the vanishing locus of a set of polynomials. A point on a variety set if it's singular, if the Jacobian matrix at that point drops rank, and the stratification would be a filtration over dimension such that successive differences are either empty or smooth manifolds. And these manifolds should have pure dimension. Such a manifold will be called a strata. And additionally, we will want this decomposition to be equisingular. This means that the local geometry around points should stay constant. So this variety here, called the Whitney umbrella, clearly the singular locus is just this line, but the origin here has very different local geometry compared to anywhere else on this singular locus. We would like to find a way to detect this origin as special. And this is done by something called Whitney stratifications. So again, we start with a filtration X-bullet, and the successive differences are now I-dimensional manifolds. And such a filtration is called a Whitney stratification if it satisfies what's now called condition B. So we pick two strata, M and N. M is this two-dimensional sheet, N is the line. We pick the point Y here. We take a sequence on M, a sequence on N that converges to Y. So condition B is that if we have a limiting set of secant lines and a limiting tangent plane, then if Whitney's conditions should hold, then L should be a subset of the limiting tangent space. Clearly, this fails here. The limiting tangent space is perpendicular to the wall. So the origin has to be considered as a different strata in a Whitney stratification. This can be done on a computer, and we have a Whitney stratification package in Macaulay 2, where if you just Whitney stratify this variety we just looked at, you find three components: the two-dimensional part, the line, and the origin. Let's now go back to what we looked at in our example. So in the characteristic cycle that was described by co-normal varieties. So in typical NEMA fashion, let's try to find a question to which co-normal variety is the answer. So the question here would be, what are the possible tangent spaces at a point? First, we introduce the notations that X-reg is the smooth part of a variety, and the co-normal variety is simply a pairing between, take a smooth point, you look at the tangent space at that point, and pair that point with the normal vector to that tangent space, and then you take the algebraic closure. The co-normal map will be the projection from this variety in the cotangent bundle down to the original variety. And the fibers of this map now consists of all the hyperplanes containing a tangent space or a limiting tangent space at a point. So for example, here at the smooth part of a variety, the fiber is just this tangent space, but here at the singular part, the fiber will consist of two components, one for each possible tangent space at that point. Equations for this variety can be written down using Grosvenor bases, or not calculated, I should say, using Grosvenor bases. The second thing we had was the components of the constructible functions, which were these Euler abstractions. The question here would be, how singular is a variety at a point? Euler abstraction is just one answer to this question. I will not give you the technical definition, but just give you some of its properties. That the Euler abstraction is equal to 1 on the smooth part of a variety. And if I have a one-dimensional variety, so a curve, then the Euler abstraction is just a normal multiplicity of the curve. And if my variety is a hypersurface with isolated singularities, the Euler abstraction will produce something called the Milnor numbers. Let's look at our umbrella again. Then here we have it has three strata. So the Euler abstraction for the two-dimensional strata is generically 1. It is 2 everywhere on this line, except at the origin where it happens to be 1 again. And then you can do similar exercises here. So let's continue with this example now. So we look at this variety y defined by a very simple polynomial, and I look at the system of PDEs that annihilates this polynomial raised to the generic power. Then I want to find the function that is constant on this variety y. And this can actually be calculated in terms of Euler abstractions now. So I just have a simple linear system. I have one everywhere in my variety. I have my Euler abstraction, and I have some unknown functions that I need, unknown numbers that I need to fix. I solve this, and I get just 1, 1, 1, 1. So this means that the constant function of this variety is just this combination of Euler abstractions. Why do I want this? Well, it turns out that the characteristic cycle of this variety, so the system of PDEs that annihilates this polynomial, is the constant function on entire space minus this characteristic function that we just calculated. So we can, of course, now just write this as the Euler abstraction of the entire space minus the Euler abstractions we just found. And using the pairing we did before, where we could just replace Euler abstractions by conormal varieties, we find that the characteristic cycle given by this, and I try to show these here. So the conormal variety here is the entirety of the two-dimensional sheet, and then you have all the possible normal vectors. This conormal variety is the line and all orthogonal planes. And here you have a C urgent here, so you have the origin somewhere in here and every possible direction around it. So how do we do this for Feynman integrals now? The interesting variety here is the variety of the integrand. And if you use the Pomeranski form, we first homogenize to also capture the singularities at infinity. So we look at the variety that lives in the product space of integration variables and kinematic invariants. We look at the system of PDEs that annihilates the integrand. The characteristic cycle of this PDE is, as we saw on the last slide, given by the difference of the characteristic function of the ambient space minus the characteristic function of this variety. So this has a decomposition as in terms of Euler abstractions that we can actually calculate explicitly. So what we need to do is Whitney stratify y. We calculate the Euler abstractions. We interpret this as a linear system, and we solve for the M alpha, and we then can just collect this into the characteristic cycle by being just the parts where M alpha are non-zero. Now we have a full description of the singularities of the integrand. Let's now go to integration. We interpret integration very simply, just as the projection from this space of integration variables and kinematic variables to just a space of kinematic variables. We obtain the constructible function for this system of PDEs that annihilates the integral from the system that annihilates the integrand by just push forward this projection. And its action on characteristic functions is just given by taking the topological Euler characteristic of the fibers of this map. So specifically for our constructible function we had here, it just becomes n plus 1, n being the dimension of the project space minus this Euler characteristic. And also on the characteristic variety, the action of this map is just that we take the defining equations of the characteristic variety of the integrand, we add the origin in the dual variables of x. So these are the xi's, so these are the Fourier transforms of x, and then intersect with just the z. So now we get the characteristic variety for our integral as well. The Lambda singularities now, by definition, is just a singular locus of this D module. So we take this characteristic variety we just wrote down, we remove the zero section and project down to just the kinematic space. We take the algebraic closure. If we now denote our proper push forward with chi, which, as we said before, was the rank function of this D module, it can be decomposed into this form. We have some non-zero number here, mu naught, times the minus the constructible function that is supported on the singular locus. Mu naught here is the number of master integrals for generic kinematics. And in fact, this rank is the number of master integrals for every kinematic, where every is that I am ignoring, like if you have 6 or 7 point functions, you would need to include gram determinant constraints for external kinematics. That's ignored here. So we can actually calculate this explicitly. We calculate the singular locus Z as the variety of this ideal. So we took our defining equation for the characteristic variety. We remove the zero section and we project down to the kinematic space. And this is the variety that is the Lambda singularities. We can witness stratify this variety and calculate the Euler obstructions. We can calculate the Euler characteristic now for one Z in each strata. And we treat this equation as a linear system again and solve for the multiplicities. So again, we obtain a constructible function or equivalently characteristic cycle for this D module. That's weighted like this, where we just need to include the things with non-zero multiplicities, mu alpha. Let's look at another example now. We have this entire framework. Let's look at a two-mass sunset integral. So we have one mass equals 0 and two different masses. This has the same lambda singularities that we have already seen, the lambda singularities for the bubble. Each kinematic invariant goes to 0 and the zero locus of the Chilean function. However, this full now microlocal description of singularities that we have looked at is actually much, much more richer than it was for just the bubble integral, even though it has the same singular locus. So we're going to look at it here. If we try to calculate the constructible function, what we end up with doing is solving this linear system. So this is the Euler, these are the Euler obstructions for the singular locus Z. These come from the Euler characteristics of the fibers we needed to calculate, and we get these multiplicities here. So the constructible function now is 4. It starts with a 4 because this integral has 4 master integrals. And then we have the codimension 1 pieces that we saw before that also appeared for the bubble, but now weight by 2 here. But we also get a codimension 2 and codimension 3 pieces. So the characteristic cycle for this PD looks like this now. And this is maybe not a surprise for us because we of course know that the two-mass sunset integral is a much more complicated object than the one-loop bubble integral. So just to summarize, what we have seen is that the singularities of a system of PDEs can be described by a constructible function or equivalently a characteristic cycle. This knows the lambda singularities. It knows the number of master integrals on and off singularities. And it tells us that the solution to the system of PDE is microanalytic outside of this characteristic variety. And all of this is implemented in Macaulay 2, and the software is available here. Thank you.